So I'm very pleased to introduce Reid from Houston, from Rice University, and he will speak on representation rigidity to profinite rigidity.
Thank you, Gopal. Is this on? Thank you. Thank you, Gopal, and thanks to the organizers for the kind invitation to come and speak here in Bangalore. I also must thank the organizers for their fortitude in organizing this conference. It was originally scheduled for April of 2020. COVID happened, and then periodically we would get announcements about the conference is going to happen. Conference is going to happen, and thankfully Gopal, Andrei, and Sury, and Andrei, Tralle kept on pestering everybody to have this conference, and it's great to be here in Bangalore and seeing everybody here. Okay, so I'm going to talk about representation rigidity to profinite rigidity. And this kind of representation rigidity was essentially mentioned in Emmanuel's talk earlier today in the guise of Galois rigidity, and I'll explain what that is shortly. But what I'd like to do is I talk about the motivation, which is about profinite rigidity. So this is sort of ongoing work with Martin Breitson. We've been working on this for quite some time now, and the stuff I'm going to talk about today is also joint with some of it with Ben McReynolds and also with Wayne Spittler. So I'm going to start by talking why we're really interested in this notion of representation rigidity and the application of to it for profinite rigidity. Okay, so if you're a geometric group theorist these days, you kind of like groups to act on things. Whether that's if you're thinking about discrete groups acting on hyperbolic spaces, or linear transformations acting on vector spaces, or perhaps the most basic case is when you got a group that's infinite, it's acting on finite sets. So you get finite quotients. And the kind of question that we're interested in is to what extent that can recover the whole group up to isomorphism. So the basic question is to what extent finite quotients of an infinite group gamma recovers gamma. Up to isomorphism. So that's kind of the basic question. It's a question you can talk to undergraduates about, and they'll object immediately, and they're going to say to me, well, wait a moment. There's infinite groups with no finite quotients. And so we're going to pretend that such things don't exist. We're only going to work with groups that have a rich supply of finite quotients. So a standing assumption is that all discrete groups gamma are, first of all, finitely generated, and to ensure a rich supply of finite quotients residually finite. Which you probably all know, but I'll write it down anyway, means that if I give you some non-trivial element gamma and gamma, so if gamma belongs to gamma, and it's not the trivial element, then I can find a finite quotient of gamma that recognizes that gamma is not the trivial element. There exists phi from gamma to A, where A is finite, and phi of gamma is not the identity. And so we are all familiar with large classes of residually finite groups. And I'm going to just mention classes of groups that tend to live in Houston, Texas, in my office. I'm sure there's lots of other groups that maybe live elsewhere in the world. So finitely generated linear groups. Are residually finite. That's really just Maltsev's theorem. Things that are close to my own heart are the fundamental groups of compact three manifolds. I mean, this is kind of relatively straightforward. This one's deeper. It uses the geometrization conjecture solved by Perlman. But anyway, these guys are residually finite. And other groups, maybe such as a mapping class group. Or so these guys are residually finite. Okay, so what's profinite rigidity? The definition. So and again, let me just circle this in orange. So this is the standing assumption. So if I don't say it, it's there. Okay, so don't say, well, wait a minute, there's a group finitely generated and residually finite, because it is. Okay, so a group gamma is profinitely rigid if whenever we have lambda is another finitely generated and residually finite group is such that, well, the naive way to say it is that lambda and gamma have the same finite quotients. So maybe let's write that. Lambda, gamma have the same set of finite quotients. But that's not a terribly useful way to phrase this. A more useful way to phrase it is in terms of the profinite completion of the group that packages all the finite quotients of the group into a useful object, such that such that lambda hat is isomorphic to gamma hat, then this implies that lambda is isomorphic to gamma. So the profinite completion, so if you haven't seen the profinite completion before, there's nothing I can usefully tell you in the next couple of minutes that's really going to cheer you up at all, other than to say it's a very useful tool for packaging the finite quotients together. It has topological incarnation in that it's a compact Hausdorff totally disconnected topological group. Now, that may not cheer you up either. And the point is that the whole deep connection between the discrete group and the profinite group comes between this correspondence between finite index subgroups of the profinite guy, or open subgroups maybe in the old days before Nikolov and Siegel, and finite index subgroups in the discrete group. So just to kind of write down the definition is that gamma hat is equal to the inverse limit. If we look at normal subgroups, so N here will be the normal subgroups of gamma of finite index of gamma mod N. So if you look at the subgroups of normal subgroups of finite index inside gamma, this turns into a directed set. You can construct an inverse system out of that using reverse inclusion, and then you get this profinite completion as the inverse limit. So it's just this giant object that captures all the finite quotients in an organized fashion. I'm sorry? On the face of it, there's no connection between lambda and gamma. All we're saying here is, here's the profinite completion if we're in this room. Here's the profinite completion in that room. I'm telling you they're isomorphic. The task is to decide whether lambda and gamma are isomorphic. An abstract isomorphism, yeah. Right, so in the old days, this would be continuous isomorphism. But because of Nikolov and Ziegel's work, you can just assume that this is an abstract isomorphism. What? I mean, all I'm asking here, or maybe I'm misunderstanding what the question is that not necessarily. That's kind of the question. Yeah, so the question is to decide when it descends to an isomorphism, and in fact, in general, we don't expect that to be the case. Maybe you can, and maybe you can't. There are groups with the same profinite completion without there being an isomorphism. Is that what you're asking? Yes is the answer. Yeah. Sorry, maybe I misunderstand the question here. No. Exactly. And that's really the challenge here. Okay, all we're given is an isomorphism at the level of profinite completion. You have to decide whether there's an isomorphism. Okay. It may come in a way that's just mysterious. It may just be that, I've just told you there's an isomorphism here, and then just by some magical construction, I've proven these guys are isomorphic, and it may be nothing to do with the one. We're all happy. Okay, well let's get even happier here. Okay, so let's prove that Z, the infinite cyclic group, is profinitely rigid. Now, this is not difficult, as you could probably done it in your heads by now, but let's just talk through it, because I'll say something shortly that should give you pause for caution. So why is Z profinitely rigid? Well, so suppose we've got lambda here with, lambda hat isomorphic to Z hat. Okay, well, lambda on the face of it could be non-abelian. Well, if it is non-abelian, so let's say case 1, lambda non-abelian. So this implies that, there exists a commutator that's non-trivial inside lambda. Now, what have I told you? The group's residually finite. It's got the same profinite completion as Z hat. So therefore, all we see are finite cyclic groups here is the finite quotients of this guy. So all we see for the finite quotients of lambda are just finite cyclic groups. Any commutator dies, and so therefore, that's illegal. But all finite quotients of Z are cyclic, and so the commutator dies. Okay, so now then the group is abelian, so therefore lambda is abelian. So it's a finitely generated abelian group. So the structure theory for finitely generated abelian groups tells you then, well, there's a free part and a torsion part. Well, if it wasn't just Z, you can visibly cook up a finite quotient that would be illegal. So this implies then that lambda is isomorphic to Z. And, so there we go. That was easy. And in fact, you can kind of see from here that this holds more generally for finitely generated abelian groups. So that's a class of groups that we've proven are profinitely rigid, albeit it wasn't very hard to prove that. On the other hand, I'm not going to get into this in any way. There are non-examples, and this is due to Baumschlag. And Baumschlag's examples are things that are virtually Z. So you have two finite extensions of Z with the same profinite completion, but they're not isomorphic, but they contain Z of finite index. So that should worry you, right? If you've got Z as a finite index subgroup, but I'm telling you, you can construct these groups with the same profinite completion that are non-isomorphic, indicates a certain amount of subtleties involved in this business. So there exists groups that are virtually Z with the same profinite completion. But they're not isomorphic. Now, I could go on and sort of describe a litany of examples and talk about nilpotent groups and all sorts of other kinds of groups where one understands things fairly well about when you can construct guys with the same profinite completion, how many groups are there with the same profinite completion. But I'm not going to do that because the kind of motivation for us is the following basic open question. So our motivation is the following thing, and this is a question that's due to Remesselnikov from the 70s that asks, is the free group, and we may as well assume that the rank's at least 2 now by this point, is the free group profinitely rigid? Okay, so this sort of very innocuous sounding question, and maybe to make it even more innocuous, so here's a free group of rank 2. So all the finite quotients of the free group of rank 2 are all finite groups generated by at most 2 elements. So we're asking, is there this weird group out here that maybe has 100 generators, all of which its finite quotients are precisely the set of finite groups that can be generated by at most 2 elements? And this remains unknown. I think, at least for Martin and myself now, I think we believe conjecturally that the answer to this may be yes. And again, from the eyes of low-dimensional topology, the free group arises very naturally as a fundamental group of compact surfaces with boundary. And we could think about other cases that generalize that to fundamental groups of compact surfaces without boundary. And so we could ask question, is phi1 sigma g, I'll just say g bigger than or equal to 2, orientable, just because I like orientable. Is this guy profinitely rigid? And another version of this would be if M is a finite volume hyperbolic 3 manifold, is pi1 of M. Profinitely rigid. And again, I think, well, at least for Martin and myself, I think we kind of believe the answer to these questions are also yes and yes. Beyond that, I wouldn't dare to say anything. I mean, there are examples of Matthew Stover's of complex hyperbolic lattices in SUN1 that have the same profinite completion but are not isomorphic. So anything beyond this kind of setting, I'm not really prepared to say anything. One could also kind of generalize a little bit further than this. So these surfaces are uniformized by discrete groups of isometries of the hyperbolic plane. And these are often called Fuchsian groups. So we could even ask whether finitely generated Fuchsian groups are profinitely rigid. And similarly, we could also go to the 3-dimensional one and ask about finitely generated Kleinian groups. And again, if you're of a low-dimensional topology vent, which I am, you might wonder about 3 manifolds more generally, and it's just not true. So profinite rigidity fails. Or even for geometric 3 manifolds in the sense of Thurston. So there are examples of Zipher fiber spaces and torus bundles over the circle for which the manifolds are not homeomorphic, but the fundamental groups of the same profinite completion. Okay, so I'm going to mention two theorems. Theorem one is the older theorem that Emmanuel kind of mentioned in his talk today. And then theorem two is what I'm going to sketch some ideas about later, following some of the ideas in the proof of theorem one that gets to the heart of this role of representation rigidity. So theorem one, so this is with Bridson, McReynolds, myself, and Spittler, that there exist arithmetic lattices in PSL2R and PSL2C that are profinitely rigid. And I'll talk about some of these examples shortly. We only have finitely many by our methods, and you may wonder what finite might look like. Is it 17 or the number of atoms in the universe? Well, it's closer to 17 is the right answer. So it's a sort of very useful tool, but somehow it has limited applications, but it's still enough to provide the first examples that are groups that are like free groups that are profinitely rigid. Yes, there are. So one could put manifold there as well. And I'll get to some examples shortly. Okay, so that's the first theorem whose proof I'll describe a little bit because it feeds into the later stuff. And then the second theorem, which I'll state somewhat vaguely for now, but I'll state more precise versions as we go along. So Martin and I have spent a lot of time thinking about profinite rigidity, what it might mean for various classes of groups and what you can detect from the profinite completion in various ways. An elementary consequence of this kind of argument here kind of says if you've got two groups with the same profinite completion, there are Booleanizations of the same. So it's a very kind of soft thing to state, but we're interested in sort of deeper properties of what the profinite completion might see. And the theorem that I'll state, so theorem two, this is kind of the vague version. And it says the following: there exist finitely presented groups that are profinitely rigid amongst finitely presented groups, but not amongst finitely generated groups. So the profinite completion can sort of see this subtle distinction between finitely presented versus finitely generated. Any more questions? I'll motivate this. Will I motivate it now, or will I motivate it shortly? Yeah. Right, exactly. So exactly right. So that's good examples of guys with the same profinite completion. So just to say what Venki said there. So again, as Rajan mentioned in his talk, there are these arithmetically equivalent number fields that have the same zeta function. And one way to kind of parse that is that, you know, the splitting types of primes are the same. Maybe you want to say adelically equivalent rather than arithmetically, but roughly speaking, there are number fields for which the primes behave the same. If you take SLN of the rings of integers of those things, then the finite quotients are all the finite quotients, assuming the congruent subgroup property, but you can arrange those number fields to have those properties. And so therefore you get guys that are not profinitely rigid, and they have the same finite quotients. Sorry, not isomorphic, and they have the same finite quotients. They're not even commensurable because the rings of integers are very different, but those are good examples. And this arithmetically equivalent will come up again shortly. Finite what now? Maybe, maybe not. It's a good question, and I'll come back to that shortly as well. But just to maybe pivot onto what Brian mentioned there. So there's the Remeslenikov open problem about the free group. Okay, so maybe what I'm doing, I'm going to wait actually. I'm going to wait till I state the theorem more carefully. But it's a very good question about why we might think about that. But I'll come to that later. Okay, so let me now talk a little bit about this representation rigidity in the context of theorem 1. So let me, right. So what I'm going to talk about here is, let me just call it the Beamer strategy. Okay, so there are various notions of what might mean by representation rigidity. A famous one being the Moster-Prasad rigidity for finite volume hyperbolic n manifolds, where n is a dimension at least 3, which kind of says there's a unique hyperbolic structure on these finite volume manifolds. Then there's Margulis's superrigidity that kind of soups that up to give, rigidity not just in the ambient Lie group, but pretty much any Lie group you put your discrete group into. And this is some weak form of this. And kind of the way to say it is Emmanuel was saying, is that there's just one orbit for the Galois group action. Now, in Scotland, we don't talk about Galois orbits. We're going to talk about counting the number of conjugacy classes. So the kind of thing that we're going to describe as kind of the minimal possible number of Zariski-dense representations into, and again, I really find it hard to get away from 2x2 matrices. Anything beyond that, I find quite hard. And I'll put a P here sometimes as well, if I'm feeling sort of dangerous. And I won't really think too much about that. But this is what we're really going to look at here. This kind of idea that we're going to look at groups that have got the minimal possible number of Zariski-dense representations. So what might that mean? So let me do an example that will be the running example for the rest of the lecture. So let's take the 3-3-4 triangle group. So in the hyperbolic plane, we can build this triangle with interior angles pi over 3, pi over 3, and pi over 4. We can take the group generated by reflections in the edges here. That gives us a discrete group of isometries of the hyperbolic plane. It contains reflections by definition, since I said it was a group generated by reflections. But I want to consider only the stuff that consists of orientation preserving isometries. And so this is what that is. So this is the subgroup of index 2 consisting of orientation preserving isometries. And it's can be presented by, let's say, 3 guys for C1 cubed, and C2 cubed, C3 to the 4th is 1, and C1, C2, C3 is also equal to 1. Or maybe you prefer the more sort of standard version generated by 2 elements here. A cubed is B cubed. It's AB to the 4th equals 1. So let's consider the collection of Zariski-dense representations of this guy into PSL2C. So let's let rho be delta into PSL2C. Zariski-dense. Okay, so what can that look like? So, so rho sends A to some matrix. Again, I'm going to abuse notation, so it'll be a matrix up the side. So where can A go? Well, A has order 3 over here. So the only possibilities are that A has order 3 in the image, or it's trivialized. But if it's trivialized, then B is 1, so the whole group gets killed. And so it's a trivial representation, so we can put that away. And so we can assume that A maps to something of this form, where omega squared plus omega plus 1 is 0. It's a cube root of unity. And then B, it's a similar statement that it can't die, so it maps to an element of order 3 here. And so in this case, because I'm looking at Zariski-dense representations, it's going to look something like this, where R is not 0, because I want to make sure that I get a Zariski-dense representation. So that's what the typical Zariski-dense representation can be conjugated to be inside PSL2C. Again, I'm only interested in characters of representations, but that's what they look like up to conjugacy. Okay, so what do we need to do? Well, AB has order 4. So AB has order 4. So where does AB go in this guy? Well, it could either go to 1, can go to element of order 2, or an element of order. Or if it maps in as an element of order 1, well, that just gives us a cyclic representation in that case. Again, not Zariski-dense. If it goes in, so we can ignore that one. If it goes in as an element of order 2, well, what's the image in this case? Well, it's 3, 3 squared equals 1. And that's just the alternating group on 4 elements. Again, not Zariski-dense. So the only possibility is that AB goes in as an element of order 4. So this implies that the trace of rho of AB is plus or minus root 2, since that's what the trace of an element of order 4 looks like in PSL2C. Now, what is this trace from here? So this is omega squared plus R plus omega bar squared is equal to, it's equal to plus or minus root 2. So we get omega plus omega bar squared minus 2 plus R is plus or minus root 2. This is just 1, because these are, when it's squared, it's just 1. So we get that minus 1 plus R is plus or minus root 2. So R is 1 plus or minus root 2. Okay, so whatever that is, we found 2 solutions for Zariski-dense representations. What's the trace field of this group? The trace field is just Q adjoined root 2. That's all that it is. So the trace field of delta is Q adjoined root 2. So by seeing the minimal number of representations, that's what we're seeing here. We're seeing the faithful discrete representation and one other representation. And this is an artifice of the fact that this delta is arithmetic. And as Rajan was saying this morning, there is a quaternion division algebra lurking around. So these 2 representations come from delta being arithmetic. It comes from a quaternion algebra from B over Q root 2, where we see PSL2R at, say, the identity embedding, and PSU2 at the other. So this is what I mean by the minimal possible number of representations. Okay, so what Galois rigidity is going to be that. So maybe in the advent, in the midst of time. So Galois rigidity, so G is Galois rigid if, okay, yeah. Okay, let me just write it, if it has minimal number. Of Zariski-dense reps. They all come from the trace field. So, so these triangle groups, in general, if we just take the PQR triangle groups, their PSL2C character varieties are all zero-dimensional. Again, why? Well, they don't split. If you've got a curve of characters, you split. But triangle groups don't split. So 237 is an example of another group which is Galois rigid. So another example is delta 237. But notice a non-example is the devil's triangle group, delta 666. So even though this thing has zero-dimensional character variety, notice that this guy surjects the hyperbolic triangle group 662. And so you get additional Zariski-dense representations from this guy. So they're not part of the Galois orbit that comes from the trace field here. So this group is not Galois rigid. So some triangle groups are, and some triangle groups are not. So it's a strong, strong version of having zero-dimensional character varieties. Let me just write down a couple of other examples that will may or may not show up. So as Emmanuel mentioned earlier, this group here, PSL2 of Z adjoint omega, so this discrete subgroup of PSL2C, this is Galois rigid. I mean, that takes a little bit of proving. The only representations are kind of the inclusion and Galois conjugacy, or sorry, of complex conjugacy of that. And just as a point, so this guy here, this contains the fundamental group, say, of the complement of the figure 8 knot. So this looks like, say, alpha beta, and it has a relation of the form W alpha W inverse is beta. So this is this one-related group that we have here. And Thurston's theory tells you that, unlike this guy, this has a one-dimensional character variety. So there's lots of Zariski-dense representations on this guy that just don't appear here. And then maybe one more example. We let MW be the Weeks manifold. So this is the smallest volume hyperbolic 3 manifold. Then pi1 of MW is also Galois rigid. So here there's a cubic number field that occurs as a trace field. Once again, this guy's arithmetic, so you see sort of the inclusion, the complex conjugation of inclusion, and a real representation that gives you a PSU2 representation from the arithmeticity. So these are examples of groups that are Galois rigid, and these are the sort of some of the examples anyway, not this one, but so where are we? So this guy here, so this guy is profinitely rigid. This guy is profinitely rigid. This guy is profinitely rigid. Getting back to Rajan's question, we don't know whether this guy is profinitely rigid, so going down is kind of non-trivial. And the methods that we have actually don't apply, so it's still open as to whether this guy is profinitely rigid. Okay, so let me just try and say a few words about what's the connection between this Galois rigidity and profinite rigidity. So what do we leverage? Let's consider the case of delta. So let's take delta to be the 334 triangle group. So the way that Martin likes to describe it is that we've got this group lambda. with the same profinite completion as delta. So again, lambda is just some finitely generated residually finite group. And it's lying in a gutter somewhere over in Scotland. It's just lying there, horrible, dirty. And our task is that we want to try and prove it really is just delta. So we've got to somehow massage it, clean it up, and then boom, it's this little crystal that turns out to be this profinitely rigid guy. So on the face of it, lambda's just living out there in nowhere land. But the Galois rigidity allows us to do the following. It says that there exists rho from lambda back into delta with Zariski-dense image. Again, because of time, I'm not really going to go into this, but from this quaternion algebra that I mentioned, it gives you a package of local representations that go into SL2 of QP bar. In fact, they go into bounded subgroups, the kinds of things that Brian was talking about, SL2 of that Z root 2 completed at various valuations. So that gives a representation or a family of representations of the profinite completion into these profinite groups that then passes to lambda hat, that then passes to lambda. So then lambda, we now have a family of representations associated to lambda that we've built from delta. But then the point is to recognize, in fact, all that you could have in this case is that it's back into delta. And there's lots of problems. And one of these problems is these arithmetically equivalent number fields for which kind of the local information, you just can't tell whether you've got that number field or the other number field. But in very low degrees, like degree 2 in the quaternion algebra is what it is over here, then we make progress. But for 2, 3, 7, we can't make progress. So this kind of strategy doesn't work for 2, 3, 7. And the reason it doesn't work is that 2, 3, 7, the trace field is q cos pi over 7. And for this guy here, it's got exactly the same congruence quotients as PSL2 of the ring of integers of q cos pi over 7. And so we cannot distinguish it using our technique. So what we can conclude is either there's a representation back into here and we win in the way I'm going to tell you, or you go back into this PSL2 of this ring of integers, and there we stop talking, because that's something we don't understand. So the point about this is now, we've got this representation, and then we come to this kind of end game. And this is a fairly general strategy. It works, for example, if you have a group with the same profinite completion as SL3Z, you get a homomorphism of the fake guy back into SL3Z. And in fact, this representation has to be faithful. And so you may as well look for guys with the same profinite completion as SL3Z from amongst subgroups of SL3Z. Now that may sound like progress, but if you've ever thought about subgroups of SL3Z, that's not really progress. We don't really know too much about that. But the good news here is that because this is a Fuchsian group, we can make progress. So here's another thing that comes out of this kind of Beamer's strategy is that, let's call the image L. Let's not do anything. So suppose L inside delta is a proper Zariski-dense subgroup. Then L has a finite quotient that delta does not have. Okay, so this is progress. Why? So this is good, because this must mean that when we look at this image here, what must the image of lambda be? It must be onto delta, because if it wasn't onto delta, this statement here would provide you a finite quotient of L and hence lambda that was not a finite quotient of delta. So what we get from here, we must have that rho now is lambda onto delta. But now we have lambda hat onto delta hat, which is isomorphic to delta hat, and we get this. But then the Hopfian property kicks in to say that that's an isomorphism, and that's where the isomorphism comes from. So the strategy is that this Galois rigidity gets you progress to get you back into some group you like. That's a general phenomena, but this is where some low-dimensional theory kicks in, at dimension 2 and dimension 3. Okay, well, I didn't quite get as far as I'd hoped, but never mind. Let me state the theorem, the more precise version of the theorem, and then comment on Brian's question about Did we expect that or not? Okay. The question? So theorem 2, maybe theorem 2 prime. And this is the more precise version that we have with Martin and Spittler, that right, so there exist finitely presented groups gamma such that 1, gamma is profinitely rigid. 2, gamma cross gamma is profinitely rigid amongst finitely presented groups. And then 3, there exist infinitely many lambda n such that lambda n is finitely generated, and lambda n hat is isomorphic to gamma cross gamma hat. Moreover, in fact, in 3, what we have is we have inclusions of lambda n into gamma cross gamma that induce an isomorphism, lambda n hat, gamma cross gamma hat. So in the language that's now become kind of standard in this area, this would say that gamma cross gamma, comma lambda n, is what's called a Grothendieck pair. So way back in the 70s, Grothendieck asked the question whether an inclusion of finitely presented residually finite groups could give you an isomorphism at the level of profinite completion without there being an isomorphism at the discrete level. And Platonov and Tavgan gave finitely generated examples. And these were lambda fg with lambda contained inside fn cross fn, the free group. So we would have lambda hat isomorphic to fn plus fn hat, and then Bridson-Grunewald actually answered Grothendieck's question by constructing finitely presented examples. Now, to get to Brian's question, so suppose we kind of knew that you know, Fn was profinitely rigid. Well, okay, you may think about Fn cross Fn. These guys here, these are never finitely presented. So it's an old theorem of Baumschlag and Roseblade that finitely presented subgroups are kind of closed in the profinite topology, so that you can't have them having the same profinite completion as the ambient group. And so maybe that's kind of a hint of things that are going on, that this kind of construction that people have of these Grothendieck pairs, finite generation was easy to build into it. You can get finitely presented cases, a la Bridson-Grunewald, but in fact, one of the motivations for us was this kind of Platonov-Tavgan construction and the role of the free group cross free group. And so we began to wonder, can one actually prove a theorem with various groups that allows us to conclude something like this? So what is gamma here? Well, gamma is going to be pi 1 of m. Now, I would like to say m hyperbolic, but I can't say that. But m is a Seifert-Fiber space over S, where S is H2 portioned out by delta. So Seifert-Fiber spaces, so this is going to be a closed-oriented three-manifold that's foliated by circles. You collapse the leads down, you get a two-dimensional orbifold. So this S looks like this, where you see these cone angles here. These cone points correspond to the so-called exceptional fibers, and then the regular fibers give you the rest of the stuff. And so as far as we're concerned here, maybe the group is of the form gamma to delta to 1. It's a short exact sequence where this infinite cyclic group is generated by any regular any regular fiber. So this is the theorem. I had hoped to say a little bit more about the proof of the theorem, but the proof of the theorem executes the Beamer strategy in the sense that we're going to use Galois rigidity. Now, what could that mean here? Well, M's a Seifert-Fibered space, so Galois rigidity is what you think it might mean. Any Zariski-dense representation of pi1 kills the center, so it factors through delta. So there's this shadow of Galois rigidity you see for delta in the Seifert-Fibered space, and you can leverage that to run the program that I kind of described earlier. Gamma cross gamma is a little bit more delicate. It's not kind of Galois rigid in the sense that we described, because you can project on both factors, but there's enough of Galois rigidity around for where we can make progress to kind of prove that the hard thing is to show that anything with the same profinite completion as gamma cross gamma includes into gamma cross gamma. Getting infinitely many, that's kind of this souped up construction. It's a good deal more delicate, but it's part of this general framework that people have used here, the magic words of fiber products. But it is quite delicate. You may wonder, well, why did I take Seifert-Fibered spaces rather than delta? Well, this fiber product game that Martin's an expert in, we like things where H2 is 0, okay, for various reasons. H2 of delta is not 0, but this is a closed 3-manifold, so H2 is 0. And so therefore we can make progress here with the Seifert-Fibered space that we couldn't just with delta. We'd love to put the fundamental group of the Weeks manifold here. We can't do that because we don't understand in the same way what finally presented subgroups look like of the product of two Seifert-Fibered spaces. Again, that's kind of well understood. If you take the fundamental groups of closed hyperbolic 3-manifolds here, we don't really understand what finally presented subgroups could look like. But I think I've spoken enough, and I'll stop there because the bell went. Thank you.
Questions? You know, there was a paper by Hyman Bass and Lubotsky.
Indeed.
Which gave construction like gamma cross gamma or something like that.
No, exactly. So this was a counterexample to Platonov's conjecture.
Pardon me?
It was a counterexample to Platonov's conjecture.
Yes.
So it was exactly the same framework they used. They used fiber product construction. They liked H2 being 0 as well.
Yes.
It's exactly the same framework, Gopal.
Yeah, that's what I remember.
Yeah. You remember correctly. That's a serious question. I mean, the answer is no. I mean, I'd love to know something about mapping class groups, but they're too complicated. I'll echo my earlier statements that I like 2x2 matrices. And, you know, mapping class groups are even harder than 3x3 matrices.
They may not be residually finite.
But if you're just talking about SUN1, for example, I mean, but again, as Emmanuel said in his talk, if you take something like SUMN, where N's not 1 and M's not 1, you get super rigidity and then Galois rigidity kicks in. But if you're asking the stuff where it's SUN1, well, I mean, that's kind of problematical, I think. Maybe there are Galois. I mean, some of these fake projective planes are almost surely Galois rigid. There's problems, you see, that, you know, Stover has these examples of lattices in SUN1 that are not isomorphic, but they are profinitely isomorphic. And I forgot, he did something about projective planes as well. If he was here, he could tell us.
So what are you saying about fake projective planes?
Right, so probably some of this, we can check with Stover once he's let loose from COVID isolation.
Pardon me?
We can check with Matthew when he's let loose from COVID isolation, but I'll bet you some of these fake projective planes are Galois rigid.
Yeah, he has, I think,
He
just
has
a
a paper.
few which are not.
Right.
Okay, any other questions?
Yes. In fact, there's finitely generated groups where there are uncountably many groups with the same profinite completion. You can build these out of these kind of automata-like groups. But we don't. So if you're asking about the kinds of guys I was talking about here, I mean, I believe that these examples are all profinitely rigid, but you could ask maybe about other classes of lattices in semi-simple Lie groups. So again, getting back to the examples that Venki mentioned, there you get a finite kind of number with the same profinite completion that are come from linear groups, but there could be these weird groups out there that we know nothing about that could all have the same profinite completion as these guys. So there could be infinitely many. I don't believe it for a minute, but it's kind of hard to answer these questions.
Any other questions? Okay, we thank Alan again.
Thank you.
Thank you, Professor Gopal Prasad, for sharing this session.